going to take a look at a couple of the convergent and divergent series questions from 12.7. These are nice ones, 21, 23, and 29. 21, a couple things jump out at me here. First of all, this is very similar to n cubed over n to the fourth, which of course would simplify down to 1 over n, which is the harmonic. If you remember, the harmonic diverges, okay? Now, you do need to check if you have a divergent series, the series that you're trying to show diverges needs to have terms that are greater than or equal to the terms of the series that you know for sure is divergent, okay? But notice, we have a -1 in the denominator here. If you make the denominator of a fraction smaller, like if I have 1/3 and I subtract 1 from 3 and I get 1/2, the fraction becomes bigger. So these values, because the denominator is smaller, these values are larger than the values of this divergent series, okay? So if I've got a series that diverges and I've got a bunch of terms that are greater than or equal to the terms of that series is also going to have to diverge, okay? The other thing here, hopefully it occurred to everybody that you could take the integral of this. So you could look at the related function, which of course would be continuous, whereas this is just defined for 2, 3, 4, 5, 6, 7, and so on. You could take the integral of x cubed over x to the fourth minus 1 dx. Remember, for a lot of these problems, you've got 2 or 3 different ways you can do it. And so, of course, the derivative of the inside function here is 4x cubed. We have an x cubed, okay? Bring that off to the side. We need a 4x cubed, okay? We're going to have to pull 1/4 out here. And we're going to take the integral here from 2 to infinity. And anyway, reverse the chain rule there, derivative of the inside function goes away. It's going to be a natural log of the absolute value of x to the fourth minus 1, technically times a fourth, okay? And we're going to evaluate that between 2 and infinity. Anyway, though, if you think about it, natural log of infinity is going to approach infinity, so that's also going to diverge. So at that point, we're pretty much done there with 21. So again, be on the lookout. If you can integrate it, you should be able to do it, even if you can't get something else to work out. All right, 23. I actually kind of got caught off guard by this one. I know that the cosine function is always between -1 and +1, so I was thinking, well, you know, I could just compare this to 1 over n, and it would end up being divergent. But the problem here is the terms of this would need to be greater than the terms of this, and those numerators are always going to be 1 or less. So I have a lot of terms that are less than that. And there's also the issue if this generates negative values potentially as well. I don't know how that would come into play here. So anyway, I actually cheated, looked at Forrester's solutions for this one, and I realized this is not a continuous function, okay? We're just substituting values starting at 1 and going to infinity in here. So sometimes listing out a couple terms will allow you to see what happens. This is one of those cases. So cosine of pi, if you think about the cosine function, the cosine of pi is, the cosine is 1 at 0, at pi over 2 it's 0, and at pi it's going to hit -1. So when n is equal to 1, it's going to be -1 over 1, which is -1, okay? If we put in a 2 here, cosine of 2 pi will be back to 1. So you have 1 over 2 now, okay? If you notice, these are always going to be multiples of pi. So if you put 3 in here, 3 pi would be back to -1 over 3. 4 pi would be back to +1 over 4. And anyway, this is an alternating series, okay? And the absolute value of the terms are decreasing. The terms are all in the form 1 over n. Remember, the alternating harmonic series converges, okay? Which is always kind of surprising to people, but if you watch the video, you can kind of see a visualization of why that is. And so, yeah, this actually is a convergent series because it's actually an alternating series. And again, this guy here really kind of concealed that, okay? Because again, my gut instinct was to compare it to 1 over n, and I got burned, okay? Over here, 29. This one looked pretty awful. Again, I thought about comparing it to 1 over n, which is a divergent harmonic series. But once again, they're starting this at a value of 2, the natural log function will increase slowly. So like natural log of 2, natural log of 3, natural log of 4. Eventually at some point, we're going to start getting natural log values that are greater than 1. And once they're greater than 1, they're going to be making your denominator smaller. And so this eventually will have terms that are less than the terms of this, even though I think for a couple of terms maybe they're greater. And so that's kind of dangerous. It actually doesn't work as a comparison test. And again, it's weird because this is below 1 for a while, but it ends up being greater than 1, at which point your fractions start dropping less than that. So not the best comparison test one. You might be able to do a limit comparison test there, and you might be able to figure something out. Anyway, I ended up not doing this as a limit comparison test. Anyway, I realized the derivative of ln of n is 1 over n. So we have a derivative of an inside function there. So you can actually do an integral test here. Break it up as 1 over x, doing this in terms of x, and this would be 1 over ln of n, which would be ln, I'm using an x variable here, to the -1 power, and we're going to evaluate this between 2 and infinity. And so anyway, you reverse the chain rule, derivative of the inside function goes away, which is great. Raise the power by 1, you realize, oh, the power is going to go to 0, and you realize, oh, right, it's a reciprocal function with the denominator to the first power. This is going to be a natural log. So if this had been like, if this had been something like e to the x or something like that, that would just be the inside function. Or if it was like x plus 5, our integral would have been the natural log of the absolute value of x plus 5. So that's what's going to happen here. It's going to be the natural log of the absolute value of that inside function. But by the way, the absolute value is not going to be real important because our values here are all going to be positive. So I'm not going to leave it like that. And we're evaluating this between 2 and infinity. And anyway, ln of 2 should converge to something, but the ln of infinity is going to go to infinity. So even without showing the whole process there, this is going to end up being a divergent series. And so if the corresponding integral diverges, the corresponding series will also diverge. So hope that helps out a little bit with 12.7.